Hi! Now that we've mastered the use of integration and integration techniques, we're ready to attack improper integrals. Let's consider the work that is shown in solving the following definite integral. We are simply integrating 1 over x squared between minus 1 and 1, and as we can use the power rule to find an antiderivative minus 1 over x for this integrand, then FTC part 2 suggests the end result will be minus 2. This is seemingly an easy case. However, there is something wrong about the answer we're getting. How can a function that is positive, 1 over x squared, produce a negative signed area? Some of you will have noticed that 1 over x squared is actually discontinuous at x equals 0, and therefore we would be breaking the rules if we were to apply FTC part 2. So, we consider any improper integral as the result of f being discontinuous at the left bound, at the right bound, or in fact at any point between the bounds themselves. Is also called improper any integral that has a lower or an upper bound, or both, as infinity. In situation number 1, we'll look at discontinuities that occur at the left bound, so at x equals a. Now the strategy will be to replace the integral a to b by a new integral from L to b. Therefore we are putting an artificial left bound that starts to the right of a, and therefore guarantees the function stays continuous between L and b. And then we will move the boundary by a limit that brings L towards a from the right. If the limit does not exist, then the improper integral is said to diverge. If the integral converges to a number, then that would be the numerical answer. To help you visualize, here's the kind of scenario we're talking about, where we would love to integrate between a and b, but there is a vertical asymptote at a. So we will integrate from L to b, over which the function is continuous. And then the limit will move the boundary towards a while remaining to its right. So this is a right-hand limit. For example, in this integral, f of x equals 1 over root of x minus 1 is discontinuous at x equals 1, which happens to be the left bound. So notice that we have replaced the integral from 1 to 5 by an integral from L to 5. And the left bound, called L, we will move towards 1 from the right by using a limit process. Now, in terms of integrating, you would do the same steps as you would usually do. In this case, you can use the power rule to replace the root of x minus 1 divided as x minus 1 to the minus half. The integral is the first step we'll have to accomplish before computing the limit. So 2 times root of x minus 1 is an antiderivative of the integrand we started with. Bounds 5 and L can be inserted into the antiderivative, and that leaves, as a last step, the limit to be computed. As L goes towards 1, notice how the root of L minus 1 will head towards 0. And therefore, we get a numerical answer, meaning that this integral converges to 4. In case 2, we'll consider a situation where the right bound is problematic. So once again, the strategy is to eliminate the right bound and stop at a point that comes before it, so that f is continuous between a and r. And then we will move the boundary r so that it approaches point b. If the limit exists, then fine. If there is a divergence in the limit, then the improper integral itself is said to diverge. Again, to visualize, think of the integral from a to b that we're trying to apply to a function, but where b has a vertical asymptote. So rather than doing that, we will set a boundary called R to the left of B and find the signed area over that portion, and then a limit process will move our boundary R towards B while remaining to its left. For example, when integrating 1 over x minus 2, one can recognize that the integrand is discontinuous at x equals 2 itself, which is the right bound. So we have replaced the right bound 2 by a number called r, to which we will then do a limit from the left of 2. Once again, the mechanics of integration stay the same. So an antiderivative for 1 over x minus 2 is ln of x minus 2. The bounds are always applied before the limit is computed. So x is replaced by r followed by minus 1. And then finally we will attempt a limit where r becomes 2, where in this case ln approaching with a content approaching 0 heads towards minus infinity. If you recall, ln of 0 plus heads towards minus infinity. So this time, the improper integral diverges. So there is no numerical answer for it. Case 3 is a scenario where the problem occurs within the bounds. So this time the strategy will force us to break up the integral where the discontinuity occurs. So from a to c followed by c to b is actually the use of the additive interval property that we saw in our properties of definite integrals. And then we will apply strategies 1 and 2 to the individual improper integrals we have created. In other words, for the integral a to c, as c is the problem value, we will stop short of it at some point r. In the second integral, since c is again the discontinuity, we will start to its right, so at a value to the right of it, and integrate from L to B, and then we'll move the boundaries. If either of these two limits does not exist, then the improper integral diverges. Again, to help visualize, think of a scenario where we would love to integrate from A to C, but we cannot because FTC part 2 does not allow integration with a function that's discontinuous. So we will break up the problem into two signed areas, A to C and C to B. In the first case, we will stop at some imaginary boundary called R. In the second case, we will start at an imaginary boundary called L and compute the individual integrals, and then the limit processes will help us move these boundaries towards C in order to fill in the area that occurs. Here's the problem that we started off with, and that generated an answer of -2 until we realized that that didn't make sense. 1 over x squared is a function that has a discontinuity at x equals 0. So according to our strategy, we will first and foremost split up the interval -1 to 1 into two integrals that go from -1 to 0 and then from 0 to 1. We're splitting the signed area. In the first integral, 0 is a discontinuity. In the second, 0 is also a discontinuity of the integrand, and therefore they are individually improper integrals. Therefore, we will have to use a limit approach for each one. In the first integral, we want to stop short of 0 and then push the boundary towards 0, so that will be a left-hand limit. In the second integral, we want to make sure we start past 0 and then move the boundary towards 0, which will be a right-hand approach. Numerically, the problem is actually quite simple to solve. We have known antiderivatives for 1 over x squared, Then upper and lower bounds can be inserted into the antiderivatives. And finally, we will attempt to do limits for each part. Now, 1 over 0 does produce an infinite result, so neither limit here exists, and therefore the integral diverges. In our final scenario, we'll consider cases where the function is continuous but has an infinite bound, in this case on the right-hand extremity. Our strategy will be to integrate from a to some boundary called r. Because this now becomes a closed interval, we can at least apply FTC part 2 to the integral. And then we'll follow that up by a limit that moves the right bound further and further. For example, here we have an interval a to r, for which FTC part 2 can be applied. And as r is moved to the right, then the interval becomes more likely to resemble a to infinity, which was the original improper integral we were solving. Likewise, if the left-hand bound is minus infinite, then we would create an artificial left bound and move that bound further and further to the left. Finally, we could have infinite bounds at both the left and the right extremities. In that case, we will have to split up the integral into two pieces and perform individual limits on each one. The choice of the point where we do the separation is actually irrelevant. So once again, on each improper integral that have infinite bounds, we would now apply limit processes. If either of these limits do not exist, then the improper integral is said to diverge. Here's an example where 1 over x squared plus 1 is a function that is continuous for all x. However, it does have infinite bounds. The choice I've made in this video is to split up the interval minus infinity to infinity at 0. Any arbitrary choice is fine, and 0 just felt simple. The first integral requires that we replace minus infinity by some bound L, which will move towards minus infinity. The second integral requires that we replace infinity by r, the right bound, that will move towards plus infinity. Individually, both of these antiderivatives provide arctan functions. According to FTC part 2, upper and lower bounds can then be inserted into our antiderivative, and then the limits are left to be applied to the two individual antiderivatives we found, or to the two results that we found from the antidifferentiation process. Now, if you remember, an arctan function has minus pi over 2 as its asymptote at the extreme left. Arctan of x has pi over 2 as a horizontal asymptote at the extreme right. And that gives us a clue about the limits both of these will produce. In the end, we will get a final answer of pi. So this is a converging improper integral. Visually, what we have found is that the total area under 1 over x squared plus 1 is pi, and this despite the fact that we are going to infinity at both extremities and that the curve never really crosses the x-axis. So sometimes adding infinite amounts of very small areas still converges to a number. Voila, that's it.